All right, welcome back everyone to the deep dive. Today we're jumping straight into something pretty wild from the world of astronomy. A discovery that's honestly, it kind of bends your mind a bit when you think about the scale. We're talking about what might just be the biggest, the most massive black hole ever found. So for this deep dive, our mission is really to unpack this thing. Look at its incredible size, and also the really clever ways scientists figured out how to even weigh it from billions of light years away. Plus, what it all means for, well, how galaxies and these giant black holes evolve. And we've tailored this, as always, just for you, focusing on those key insights and maybe some surprising facts from the research.
And it really is about pushing limits. I mean, seriously, try to picture something 10,000 times heavier than the black hole we have right here in our own Milky Way. This isn't just breaking a record. It's something that makes you rethink the models, It hints at cosmic processes that are just, well, on a scale we're still trying to get our heads around. Really exceptional.
Okay, let's get into the numbers then, because they are just jaw-dropping. This new ultra-massive black hole, they're saying it's around 36 billion times the mass of our sun. Just let that number sit for a second. 36 billion. Our own galaxy's black hole, Sagittarius A, is about 4 million solar masses, which sounds big, right?
Yeah, still pretty hefty.
But this new one, it's like 10,000 times heavier. It's Godzilla compared to a house cat. It's just, yeah. Staggering.
And where it is, that's also fascinating. It's inside a galaxy called the Cosmic Horseshoe. Now, this isn't your average galaxy. It's one of the biggest ones we've ever seen. It's so massive, its gravity actually warps space-time around it. You get this amazing effect called an Einstein ring, where light from a galaxy behind it gets bent into a circle.
Like a cosmic magnifying glass almost.
Exactly. You're literally seeing space itself bend.
And the size, it's not just a big number, is it? It actually means something for cosmology. It's apparently right near the theoretical upper limit for how big we think black holes can even get. The study it was in, the monthly notices of the Royal Astronomical Society, puts it in the top 10 biggest, maybe even number 1. What does that mean, though? Theoretical upper limit. Is there like a cosmic rule about how big they can grow?
That's a really good point, and it connects to how confident they are in this measurement. Professor Thomas Collette, he's at the University of Portsmouth, he mentioned this. He said they have much higher confidence in this mass compared to estimates made using more indirect ways.
Yeah.
Often you're estimating based on things like how bright a quasar is, which can be uncertain. But the methods here, they give a much more solid number. So it's not just big, it's reliably big. It helps define that upper edge.
Okay, this is where I think it gets really clever. Because finding it is one thing, but weighing it, especially when it's 5 billion light years basically invisible because it's not actively feeding. That seems like the real challenge here. This feels like a breakthrough in just how we find these things.
It really is brilliant detective work. The team, led by Carlos Melo from UFRGS in Brazil, they basically combine two techniques. Gravitational lensing, which we just mentioned.
Right, the light bending.
Yeah, where the massive galaxy magnifies the light from behind it. And the other is stellar kinematics.
Stellar kinematics. That's studying how stars move, right?
Exactly.
And it's usually seen as the best way, the gold standard for weighing black holes, because you see their direct gravitational pull on nearby stars.
Yeah.
But like you said, that normally only works for galaxies that are much, much closer. You need to see those stars clearly.
Precisely. At 5 billion light years, seeing individual star movements, normally impossible. But they use the lensing effect, that natural magnification.
Like nature gave them a giant telescope.
Kind of, yeah. It magnified the distant galaxy enough so they could just barely detect the motions of the stars near its core. They saw the black hole's pull in two ways. How it bent the background light, and how stars right near the center were zipping around at almost 400 kilometers per second.
Wow. 400 kilometers. That's incredibly fast.
Oh, yeah. Across the U.S. in maybe 10 seconds, something like that.
And the really amazing part, you touched on this, is that this black hole is dormant. It's not lighting up like a quasar because it's not actively eating.
Right. No fireworks.
So they found this absolute monster purely by its gravity, its invisible presence. That really shows how powerful this combined method is for finding these, like, hidden giants.
And it's kind of funny. It was basically an accident.
Really?
Yeah, science is often like that, isn't it? They were actually studying how dark matter was distributed in that galaxy cluster. And this ultra-massive black hole just sort of popped out of the data. Like, hello?
That's fantastic. Sometimes you're looking for one thing and find something even more spectacular.
Exactly. Serendipity.
Okay, so we've got the scale, the amazing detection method. Let's zoom out. What does Finding something this extreme, tell us about the bigger cosmic picture, about how galaxies evolve over billions of years.
Well, the general idea, our current understanding, is that pretty much every big galaxy has a supermassive black hole in the middle. And the galaxy and the black hole, they kind of grow up together. They're linked.
How so?
When galaxies merge, gas and stars get funneled towards the center. This feeds the black hole. Some material falls in, making the black hole bigger, but some gets superheated and blasted out as a quasar, and that outflow, that energy blast, can actually shut down star formation in the host galaxy. It's like a feedback loop.
A cosmic regulation system.
Yeah, something like that.
And thinking about our own Milky Way, its black hole is only, what, 4 million solar masses? Seems tiny in comparison.
Relatively speaking, yes.
It's quiet now, but presumably it was active in the past. And might be again.
Oh, almost certainly active in the past. And yeah, when we eventually collide with the Andromeda Galaxy in about 4.5 billion years,
Right, the big merger.
that should funnel a lot of material inwards and could definitely light up our central black hole again. We might get our own quasar phase.
So back to the cosmic horseshoe. Why is its black hole so incredibly massive?
Well, its host galaxy is special. It's what astronomers call a fossil group.
A fossil group, what's that?
It basically means it's a giant galaxy that's already done all its merging. It's cannibalized all its significant neighbors. So you're left with this one huge galaxy sitting alone, surrounded by maybe just a few tiny dwarf galaxies. It's the end result of a whole group merging together.
Okay, I see.
And the thinking is the supermassive black holes from all those original galaxies that merged, they likely merged too, over cosmic time, adding up their mass bit by bit to create this one ultramassive beast.
So it's like the sum of many black holes from past galaxies.
That's the most likely scenario, yes. A history of galactic cannibalism leading to a black hole behemoth.
That feels really significant. Are we potentially looking at like the final stage, the end game for galaxy evolution in that kind of environment?
It certainly looks like one possible final stage, yeah.
Yeah.
For a very massive system, this could be it. And the impact of just proving this detection method works, that's huge too. Researchers are already planning to use telescopes like the ESA's Euclid Space Telescope, which is designed for wide field surveys.
To look for more.
Exactly. To specifically hunt for more of these hidden, dormant giants using this combined lensing and kinematics technique, we might uncover a whole population of massive black holes we just couldn't see before.
It really makes you wonder, doesn't it? Could there be even bigger ones out there? Silent giants.
It's possible.
And how did these things shape the galaxies around them over cosmic history in ways we haven't even thought of?
Mm-hmm.
This discovery, it's more than just a record. It feels like it's opening a new chapter in, well, black hole hunting.
I think that's exactly right. The main point here isn't just biggest black hole found. It's that we now have a new tool, a new way to probe the parts of the universe that don't shout their presence. It gives us a window into the quiet phases, maybe the final fates, of galaxies and their central black holes.
And it leaves you with that thought, if these absolutely enormous, quiet giants were hiding in plain sight, just waiting for us to figure out how to see them, what else is out there? What other profound cosmic secrets are just waiting for the right technique, the right idea to be revealed? This deep dive really showed that sometimes the biggest stories in the universe might be the quietest ones.